Good morning, everyone, and welcome to ICS SCADA 101, the first of many Percival CTF fuel frenzy training topics. And before we get into it, I hope everyone's super excited for our fuel frenzy tomorrow. Cool. Let's jump right into it. ICS SCADA 101. First of all, what the heck is ICS, or Industrial Control Systems? Quoting NIST here, an ICS is an information system used to control industrial processes such as manufacturing, production handling, or product handling, production, and distribution. So it is just a big general term used to encompass all the hardware and the software and the networks, the machinery, and pretty much everything else that goes into these systems. And these systems are designed to achieve some type of industrial objective. Say, whether that be manufacturing, the transportation of goods or energy, material refining, and many, many other industrial objectives that impact our daily lives every day. So these systems are incredibly important for our day-to-day lives, and we interact with them, maybe indirectly, on a daily basis. So, as I mentioned, these systems are incredibly complex. Let's delve into all the different components that make up these systems and break them down and see what they all actually do. So first and foremost, we have our IT and our OT. And a lot of you might be familiar with the term IT, or information technology. In this area of the technology is mainly focused on securing the confidentiality, the integrity, and the availability of our data, or for those of you familiar, that is the CIA triad. So IT mainly pertains to the front end of the operation. So a lot of the technology, the computers and the servers, and pretty much anything else you would interact with on a daily basis. On the other hand, we have our OT, or our operational technology. And this mainly focuses on the back end of the operation. So OT mainly focuses on things like controlling our physical devices, machinery, and our infrastructure. So a lot of the things you might not see on a daily basis, but are still incredibly important to our operation. And combined, IT and OT is used in the process of monitoring, connecting, and managing our industrial assets. So to help break that down a little bit more, I have a diagram on this slide that shows how IT and OT interact. So as you can see on the slide, the IT realm of technology is mainly focusing on things like our applications, any of our cloud agents, servers, etc. So again, the typical technology you would see on a daily basis. And then on the bottom of our diagram, we have our things like our sensors and our machines, industrial assets that are all managed and controlled by our OT. And in those two fields of technology usually interact with each other over some type of network infrastructure or network layer. So routers, switches, things like that. So these two technologies are working together in conjunction to complete some type of objective. And this is the first, one of the main parts of what comprises an entire complex ICS SCADA system. Moving forward, another core part of these ICS SCADA systems are the PLC, or the Programmable Logic Controller. And as the name implies, these devices are customizable, hence the word programmable, for various applications, depending on what they're meant to do. And in short, these PLCs contain things such as function blocks and data blocks, and these are the actual parts of the code, the internal machine that implement the logic and store all of the information coming in and out of them. We'll have a future training topic on this later today, but this is meant to just be a broad overview of PLCs and these ICS systems. So connected to these PLCs, you would have a lot of things in local management for things like for connected feedback. of these control devices. So things like sensors, actuators, alarms, etc. A lot of these will all be hooked up to this PLC, and the PLC will take their data, inputs and outputs, and depending on how they are programmed, do some type of action. So you can see on the bottom of the slide, just have an example Eaton PLC, and on the top there we have a bunch of leads where wires would be connected, and that's how you would connect all the sensors, actuators, alarms, etc. In the middle there, we have a little screen displaying some status information, a couple buttons that allow you to interact with the machine, and then on the bottom we have some LED status lights, just to give a picture of, or general picture of how the device is interpreting the data that is fed into it. And again, we'll go more into PLCs in a later training topic. I just wanted to give you a general picture of what one is and what its main purpose is. Moving forward, we need a way to interact with all of our IT, all of our OT, all the PLCs, and everything else that go into these systems. And we can do that through a device called an HMI, or a human-machine interface. And this is what the human operators would use to interface with the entire ICS. So these HMIs, especially the newer ones, usually provide some type of GUI application that the user can interact with and see the status of the system. So we have an example of one at the bottom of this slide here that shows a couple graphs, a couple meters, looks like a knob of some sort for some level, and even a picture there that shows possibly the physical status of the ICS. And these HMIs are incredibly powerful, and they're very, very useful for interfacing with ICS machines. Some of their capabilities include things like the ability to display status information, monitoring all the parts of the machine, and even some machine configuration. So if we notice that something might be wrong or we need to change how the machine is behaving, we could do that through the HMI. And similarly to the PLC, we'll have another training topic on this later. I'm just trying to give you a general overview of what one of these devices is. Moving forward, we have our data historian. And this mainly is just a centralized database to log all the ICS system activity. As I mentioned, there are a lot of different components all working together in these systems, and it would be nice to have some way to log all the information and be able to display it in a nice graph for us to see later. And this is the main job of the data historian. So these data historians are used for things such as to export data for analysis, statistical process control, and just future planning for these ICS SCADA systems. These help us optimize their functionality, or if we notice that something isn't performing as we would expect it to, we can see these trends in the data that the data historian is collecting. And the list doesn't end here. There are many, many other components that go into these ICS systems here. Things like our MTU, our Master Terminal Unit. And this is what's communicating with a bunch of RTUs, or Remote Terminal Units, all throughout our system here. So these communicate back and forth, transmitting data and status information, possibly configuration information, to keep the system in sync. Sometimes these RTUs are actually implemented as PLCs themselves. So sometimes some diagrams will have a PLC, some diagrams might have an RTU, some might even have both. And also there are many, many other intelligent electronic devices that go into these systems. Anything that could deal with remote diagnostics and maintenance, control loops, which we'll get into in a little bit, and again, many, many other things go into these systems. The list is very broad, but I tried to pick out a couple of the ones that you might encounter in the CTF and a couple of the main components that you'll find in these systems. So I hope this painted at least a general picture of what the heck an ICS system is if you've never heard of one, and just how complex they actually are. But given how complex they actually are, we need a way for these systems to be able to communicate. All the parts have to communicate with each other. And that's when we get into how do these all these parts actually communicate. So a lot of these, a lot of the parts of this, So a lot of the components in these systems, they use a lot of purpose-built protocols to streamline their communication. So these protocols may be ones you've never heard of before, and they were purposely built by the manufacturer to streamline different automation processes, such as process automation, building automation, or power systems automation, and again, the list goes on and on. So some of these protocols were designed to be interoperable between manufacturers. However, some of them are not. Some of them are proprietary. That might lead to a few problems. Proprietary protocols might not be as well vetted as interoperable ones. You might also experience vendor lock here. That's not to say one is better than the other, but it's just a couple of the hazards you have to watch out for when you're choosing between different types of ICS systems. And again, a lot of these protocols are also legacy technology, but they're still used today. Because as the saying goes, why fix what isn't broken? And that's true in some cases. These protocols do work, but they might have their issues. And also, you probably hear a lot about this in the news and the media, where a lot of these complex critical systems, they'd be very expensive, very complex, and very time-consuming and risky to replace. So it's not just as easy as saying, hey, we have a new system, let's swap it out for a better one, which is why many of them are still in use today. At the bottom of the slide here, I just have a short diagram showing a couple of the protocols and how all the PLCs and RTUs and everything else involved in an ICS system would communicate. So on this slide, just have a couple of examples of different types of protocols that these ICS systems use. Again, this is not a comprehensive list. These are a couple of the more common ones. I bolded the one called BACTHEN, or Building Automation in Control Networks. That is one you might encounter later in the CTF. This protocol is used for things like control heating, ventilation, air conditioning control, so all of your HVAC equipment, things like lighting, building access, fire detection, all that fun stuff. And for anyone who played in our previous CTF, you might recognize the Modbus protocol there too. Posting class? I believe we are. All right. I don't see why not. But yeah, I said there was a question in chat that I think I missed that for posting these slides, and I believe so. We could probably post them later and share them with some link. And these trainings will also be available too, pre the CTF tomorrow. So this is a lot of information. Don't forget that we will have a recording of this available for you to review back. So given all these components in an ICS system and all these communication protocols, I just wanted to paint a bigger picture and have a diagram of what an example ICS system might look like. And I wanted to note that I drew a dotted line between the IT and the OT on this diagram, signifying that that is not a hard divide. But typically to the left of that dotted line is where you would see IT in action most of the time, and then to the right of that line where you'd see OT in action, helping all of those devices communicate. But again, it's not a hard divide, and those two types of technologies work together to complete the whole system. Wanted to point out a couple parts of this diagram that are boxed in with the blue rectangles. We have a couple of the systems that we mentioned before. So in the middle square, in our supervision and network, in SCADA network, which we'll go into in a second, we have our data historian sitting there collecting the data from everything else in that middle rectangle, and of course on the right rectangle on the side there. So that's collecting all the data. And we have things like our remote terminal unit over on the right there at the top, And then we have our PLC connected to what looks like a temperature sensor of some sort, an alarm of some sort, probably signifying that if the temperature is too high or the temperature is too low, to sound the alarm to alert, hey, something is wrong. At the bottom there, we have our workstation, which seems to be connected to two other types of PLCs that's then connected to some type of just generic industrial equipment. So those two PLCs might be working together to interface with that industrial equipment there. And that's then all being reported back to that workstation. So that workstation might be something just like a SCADA computer that allows you to interface with all the PLCs and the equipment attached, or it might be something even like the HMI that we mentioned before that allows us to see the status of those PLCs in that equipment. So I just meant for this diagram to be paint a bigger picture. There's a lot of words on our slides, and just how to put everything together. This is what a system, a rather simple one at that case, might look like. So we've talked a lot about ICS systems in general, but there are different types of ICS systems. And we're going to go into one main type, but I wanted to mention the two most common types. First, we have our supervisory control and data acquisition, or SCADA devices. You might have heard that term thrown around before. And that's the one we're going to focus on here. I did want to mention, though, distributed control systems, or DCS. We have a slide on that, but I'm not going to go too into depth on that one. So just a brief mention of a DCS, a distributed control system. Mainly, these are just control systems of distributed autonomous controllers monitoring many control loops. So it's a lot of control and loops and systems in one sentence. To break it down, it is just a bunch of different control loops, which are comprised of, or they're the basic building block of a control system. So these control loops, they contain some type of process sensor, say like a temperature sensor, a controller function that takes in data from that, whatever that process sensor might be, and interprets it, and then what's called a first control element. And that is just a process that automatically tries to take in the data from the sensor and the controller function, measures the data coming from them, and tries to adjust the environment that control loop is placed in down to a desired set point. That would be set by the operator. So just a control loop monitoring the environment and trying to adjust the environment however it can to try to get to a steady predetermined state. So in a DCS, we have a bunch of those different loops with autonomous controllers all communicating. And with that, we have no central supervisory control. So all the loops are talking to each other, and that's how the system is comprised. This provides high reliability and usually a lower installation costs compared to its SCADA counterparts. And these DCS systems are used in things like manufacturing, electrical power generation, water treatment. Again, the list goes on and on and on. And at the bottom of the slide here, just have a simple diagram of showing what a control loop in a DCS would look like. So again, I'm not going to go too in depth into DCSs. The main focus of this talk, as the title implies, are the SCADA systems. So we have SCADA, the supervisory control and data acquisition. And the SCADA system's primary purpose is for just general system monitoring and control over long distances. So this allows for the operator of these SCADA systems to have much faster and quick real-time responses. Again, that is a lot easier than, say, sending an engineer out into the field site or all the field sites where all the parts of the SCADA system might be located. So to break down the complicated name of SCADA, supervisory control, you can just think of that as central control over an entire system. So that's the main contrast compared to a DCS, where we have a central control room or a central control unit over the entire SCADA system, where everything reports back to. And then the data acquisition part, that is just saying that this system collects and stores data from all of its multiple sources, all the multiple parts of the entire system. So SCADA systems, they're used in things like water treatment distribution, electrical power transmission, pipeline monitoring control, and again, the list goes on and on and on. You might notice that this list contains a lot of things like distribution and transmission and pipeline monitoring. So it's used in a lot of transportation applications, moving one thing from one place to another place and making sure that it gets there safely and securely. You might also notice that the applications for SCADA systems are very similar to those for DCS systems. You'd be correct there. In a lot of real-world implementations, SCADA systems and DCS systems work together to complete some type of industrial objective. So they're not completely separate, and they're not in all very, very different. They typically work together. So again, to paint a bigger picture, to paint the bigger idea with a picture, this would be just a short example of what a SCADA system might look like. So we have things like our sensors and any other manual inputs. Those are all connected to our PLCs and our RTUs. So again, those are the PLCs, the programmable logic controllers, and our remote terminal units. So that's taking in all the data from our sensors and our manual inputs, interpreting them, and then that in turn gets reported back to our HMI, our SCADA computer. And that's what's allowing the human operator to interpret all the data coming from our sensors and our PLCs. So, yeah, the HMI and SCADA computer, as in a previous diagram, could have been represented by that workstation that we identified before. So just some way for the human operator to understand the state of the system without looking at the raw data coming from the PLCs and the sensors. And in practice, a SCADA system might look something like this. Albeit this is a simple one, but I hope it paints the bigger picture. So on the right there, we just have a sample SCADA implementation, where on the bottom of the diagram, we have our industrial equipment. Looks like to me like possibly oil mining rigs, something like that. All connected to, again, the PLCs, which are then connected to some network, and that's all being, again, transported back to our central SCADA server, that data historian, and then, again, it's all being reported back to the human-machine interface. So on the bottom of the diagram, we have our production plant there. That's where all the magic is happening. It's where all of our materials are being conducted, monitored, and that's all being reported back. And again, to paint the bigger picture of what SCADA, the capabilities of SCADA, on the right of that diagram, we might have some temperature sensors somewhere else in the system. It might be in the plant, it might not be in the plant. That is also connected to its own remote terminal unit, and then is connected through what looks to be like a cell tower, so it could be very far away, all back to that SCADA server. That SCADA server might be interfacing with one plant, two plants, multiple plants, and multiple other sensors, all distributed across the system. And on the left of our slide here, I have a short animation of what a SCADA system might be designed to implement or to achieve. So it looks to be we have some type of tank there that's being filled up with some type of liquid. And we have a temperature sensor there, we have pressure sensors, maybe even a level sensor that's monitoring the state of that tank. And depending on if the liquid is too hot or if it's too full, too empty, there's too much pressure in the line, things like that. The tank is either being filled or drained. So to make sure we don't overfill the tank, we don't underfill the tank so the pumps run dry, to make sure that our liquid doesn't get too hot or the pipelines don't burst if there's too much pressure. So again, there's a lot of different monitoring and a lot of different components that go into these SCADA systems. And it's all meant to keep a steady state. So I hope that these slides and these diagrams kind of paint a bigger picture, at least a general picture, of what SCADA is all about, why it's so important, and just how complex it is. How many components are actually all working together to keep these systems up and running and to complete their objective. So we've been talking a lot about ICS and SCADA in general, but how does that apply to the CTF, or the fuel frenzy, or the fuel part of our CTF? So now that we understand what ICS and SCADA actually is, let's delve into the fuel SCADA process itself. Luckily, it's actually not drastically different than what we've talked about before, but we can now put it to a specific application. So I wanted to start off with just a diagram of what a fuel pipeline might look like underground, connected to all the above ground components that you would see. So on the left of our diagram, we have our wellheads, any of our material collection source. And that all gets fed through multiple various pipelines into our pump station. And then that pump station is then transporting our fuel through other pump stations to keep it moving through our tank storage, and then to our gas compressor station, and then finally to the end customer, whether it be a business, a factory, some other field site, or even our homes. So I just wanted to paint the bigger picture of what's happening maybe that you're not seeing when you drive by some of these stations. And then to focus in on what we're specifically looking at, I have another diagram here that just shows the process itself. So we're mainly going to be focusing on that pumping station and then the fuel pipeline and all of the technology and SCADA systems that are involved with the pipeline itself. Yeah, so we're mainly going to be focusing on just that pipeline. So let's jump into it. The fuel pipeline process. What is actually happening when the fuel is moving through a pipeline? Because it's a lot more complex than just putting fuel into a pipe and then having it pop out the other end. So to start, we actually have 3 different types of pipelines. First, we have our gathering pipelines. And this is just a network of smaller pipes designed to collect resources from their nearby sources, whether it be wells, mining, things like that. So a lot of smaller pipelines all converging into one pumping station. And that pumping station is what sends the fuel into our transportation pipelines. And this is what you would probably typically think of when you hear the word pipeline. These are your large, high-capacity pipes designed to carry resources really long distances. I'm talking it could be hundreds and hundreds of miles. Then finally, the transportation pipelines bring whatever they're carrying, their material they're carrying, to our distribution pipelines. And again, these are a network of smaller pipelines to distribute the product to the end customers, say us. So along this pipeline, we have a lot of different technologies all working together. We've seen a few of them in the previous diagrams, but we have things like our injector station. And this is what takes the fuel from our collecting pipelines and injects it into the transportation pipeline. So this is where fuel is like initially piped into the pipeline. And then along that pipeline, we have our pump and compressor stations. So compressor stations are used for gas pipelines, and pumps are used for liquid pipelines. And this is what just helps keep the material, the fuel, running through the pipeline. Because one pump wouldn't be able to keep up enough pressure to move fuel through a several 100-mile long pipeline. So we have multiple of them installed throughout the pipeline. Additionally, throughout the pipeline, we have our first line of defense and our first line of protection, the block valve station. And this is what can isolate sections of the pipeline by blocking the flow through that section. So you can think of these as just like large valves. They're usually installed, say, every 20 to 30 miles throughout the pipeline to isolate sections if we were to need to complete maintenance on them, or if something went wrong in that section of the pipeline, we could stop the flow through that section. Another line of defense we have through these pipelines are our regulator stations, and this is a special type of valve station that can be used to release pressure from the pipeline. They're usually installed at the downhill side of peaks and hills where pressure might be building up too high in the pipeline. So we could release some of the pressure so our pipeline doesn't rupture. And again, I might be seeing a theme here. This is just a general overview, and there are many, many other technologies used throughout our pipelines to keep them operational and safe. What a pipeline might look like in a diagram, I'm a big fan of diagrams to paint a bigger picture, is something like this. And again, we have our gathering lines, our transmission lines, and our distribution lines, all connected. Those to go through many compressor stations, any processing plants, pump stations, or underground storage. It's not pictured here, but there will also be block valves installed every so often along that main transmission line, things like that. So I hope this paints a picture of how all these technologies are working together along a pipeline here. So let's actually talk about the SCADA process used for all of these different stations and technologies. So as we mentioned, there are stations along the pipeline, and these stations also contain things like sensors, meters, pumps, valves, etc. So all the injector stations, all the block valves, all the regulator stations, they all also contain sensors and meters to be able to read their state and to make sure something isn't going wrong. And all of these stations are reporting back to their main control server via their remote terminal units or their PLCs, kind of like we talked about before. So they might be reporting things like their flow rate, their pressure, their temperature, etc. And as we mentioned, the main SCADA system, or the data historian, is collecting all this data, monitoring it, and logging it. And then we also have our operator in the main control room being able to take in all this data, view it in a nice way, and then monitor and respond as necessary. So the operator would be able to open and close valves, turn on and off pumps, etc., all from the main control room, given the data that they're seeing being reported back. And that operator would be using something like an HMI or some type of SCADA computer to perform all of these actions and monitor the system. Again, big fan of diagrams. This is what a chunk of a pipeline or a section of a pipeline might look like. So on the left there, we have your fuel coming in, either from an injector station or just another part of the pipeline. And this pipeline is highlighting what a block valve would look like. So you can see it looks like just a big valve that's able to stop fuel or stop flow right at that point. From going out from the right to either more pipeline or distribution lines or some other station. And as you can see, on all parts of this pipeline chunk here, they all have RTUs, remote terminal units, attached to them. And they're all communicating in some way, shape, or form back to our main control room, where our SCADA system and our data historian is sitting. Well, this just paints a picture of how all the different components are communicating back to our main control. And for anyone actually coming in person to our CTF tomorrow, you get to see this awesome little mock fuel pipeline creation here. So one of our engineers here, Kayla, who will be doing some presentations later, built this awesome mock fuel pipeline here to show actually the process in person and what happens and how the SCADA system is responding to the state of fuel. So on the left there, we have our mock fuel tank with quote-unquote fuel in it. And as that tank fills up, we have multiple sensors keeping track of like the level and the temperature. Those are all going into some mock pipelines that all have valves and other sensors attached to them. And all of the data in this mock setup here is being collected by a real PLC on the right-hand side there. So that PLC is taking in all the sensor data and turning on and off pumps, turning on and off valves as necessary with their status LEDs on the PLC itself and also on the board in the back. So for anyone coming in person to the CTF tomorrow, I could look forward to actually seeing this in action because it's really, really cool. So you might be thinking, SCADA systems, they're cool and all, or SCADA systems, they're confusing and all, and I'd agree with both of the statements. But why? So why are we studying all this? Why am I talking about all this for the CTF? Like, what's the point? And the main point is, these SCADA systems, they are a target, and they're a very large target at that. So what are they a target of? They're a target of attacks. They are a target of many different types of cyber attacks, and even many different types of physical attacks here. So there are many, many different ways to physically attack these devices and also attack them through the network, through cyberspace. And we can get into that. There are a lot of different vulnerabilities that these devices may or may not have. So a lot of the common ones include things like inadequate security architecture, inadequate security policies, default system configurations. The protocols that we talked about might not have any integrity checks, so you could send data to and from these devices, just kind of mock it and spoof it, and these devices would have no idea. There's no integrity checks that check to make sure that someone or something didn't manipulate communications. These devices could be vulnerable to buffer overflow attacks or any other attack like that. Could be that a lot of these devices have unnecessary services are not disabled, weak network security architecture, passwords might not even be encrypted. Again, as we mentioned, use of unsecured industrial-wide ICS protocols. We mentioned a couple of those in a previous slide. And you might think this list is a lot, and I'd agree, but the list keeps going on and on and on and on. So there are a lot of ways that these systems can be attacked, and a lot of different vulnerabilities to keep track of and to cover. So why are these systems even attacked in the first place? They are often used as the initial attack vector, and then that would allow whoever compromises them to move laterally through an organization. So the target itself may or may not be the SCADA system, but it's usually considered the easy target, a way to get into the network and then start crawling through the network. And also, these systems tend to be the easy target because they are, a lot of them, legacy systems. They're very old, and security might not have been a factor in their design. Why might these systems be attacked? Again, as I mentioned, the SCADA system itself might not be the target. And also, the reason they're being hacked, it's usually not for the sake of just attacking the SCADA system and compromising it. There's usually other motivations behind the attack. Things like financial gain, or political causes, or even military objectives. You might say that a lot of these SCADA systems, since they're legacy old technology, why not replace them? And we mentioned that it could be risky, expensive, and time-consuming to replace these massive systems. We also have to consider that newer technology is not just some magical solution. So it's not going to fix all the problems. Newer technology might fix some of the older vulnerabilities, but they also create new problems simultaneously. A lot of the new technology is connected to the cloud, so you have things like your cloud computing and all of your Internet of Things. All these new technologies, they create centralization in the cloud. They provide efficiency, but they also...
Connected successful. There we go. Should be coming back up.
Right back? Oh, there we go. I think we're back. Okay. Can everyone hear me? I think we're back online.
Version part of the program. Yeah. Alrighty.
Good to go. Cool. Awesome. Apologies about that. Cool. Okay, so I think probably lost me somewhere in the middle of the slide. Just as a quick recap, what happens when one of these SCADA systems is attacked? Just a quick overview again. The attacker might be looking to make system and or operation changes, altering the PLCs and the RTUs just to change the behavior of the system and possibly even to change the information that they're reporting back to the operator. So this might introduce things like false positives and false negatives. So if something is going wrong, the operator might not know because the devices, their traffic is being manipulated to report saying, hey, everything's good. On the flip side, these devices might be reporting saying, hey, everything is broken, everything is wrong. So engineers and safety personnel and anyone else might be dispatched to the field just to learn that nothing's actually wrong. And that wastes time and money. Misinformation can also be used to hide malicious activity. So the attackers might be trying to cover up after themselves. And hide what they're actually doing. And even on a worse note, system and operation changes might actually prevent the safety controls from running. So if something were to go wrong and there were safety implementations in place, those might be prevented from actually running. So more damage would be caused to the system as a result. Oh, I see in the chat we lost to a slide back. Let's see if we can go back. So this slide, just as again, a quick overview, just talking about how you might think that the SCADA systems, they're old, legacy technology, why not just replace them? We talked about how that is risky, expensive, and time-consuming, but new technology isn't just some magical solution that's going to fix all of our problems. Newer technology, a lot of it's integrated with things like the cloud and IoT. So that creates centralization, and the cloud provides efficiency, but it also creates a more singular attack vector. And things, especially with IoT, we have a lot more devices and parts of the machine that could be connected directly to the internet, which provides actually a lot more attack vectors for some adversary to attack, and a lot more things that we have to keep in mind with security. So it might fix some of the old vulnerabilities, but it creates a lot of its own new problems that might not be as well understood or studied yet. Cool, and we covered this slide about what happens when one of these systems is attacked. And after or during one of these systems when attacked, what are the consequences? Could it have things like data theft and ransomware, as these systems would be able to be compromised? It also could be a result of industrial espionage. So it might be some market competitor trying to create downtime in an operation, or cause catastrophic damage to the equipment. This could also interrupt things like resource delivery to like critical field sites, or even just to normal citizens like us. If a gas pipeline breaks that feeds a bunch of towns and cities, then whoever's living there might not be able to get the gas that they would need. And on a more negative note, this could lead to a lot of bad things like loss of life, the inability to receive critical resources, things like for gas lines, if there's ruptures and explosions, or just dangerous situations in general might be created. Dangerous situations might be things like the disaster itself, pollution released into the water that animals and humans are ingesting, or even just the process of fixing any damage done to these systems or pipelines. Say, for instance, like underwater pipelines. It's not an easy and safe job to be able to fix those. So things like that. The consequences of the attacks on these systems can be pretty grave. So given that, how can we protect our SCADA systems? A couple of defensive strategies to help protect them. First things first, assume compromise. Don't assume you are currently compromised, but just assume that in the future that compromise might happen. If you assume that your security measures are perfect and are going to stand up to every type of attack, that's the first downfall. And with that assumption, you want to develop countermeasures. So you want to be able to preemptively secure against known exploits. So if you know of an exploit that is currently being exploited in other systems, you want to be able to patch your systems before it happens to you. If you are compromised at some point, you want to be able to identify it and respond to incidents quickly. You just don't want to be a sitting duck waiting. The faster you can identify and respond to incidents, the less damaging they can be. In a similar vein, you also want to contain the breach and prevent the loss of sensitive data as much as possible. Again, you just don't want to sit back and wait. And after a compromise is complete and you've secured your systems, you want to get retrospective post-breach and apply any information you learn and any updated practices to prevent a similar attack from happening in the future. That's the worst thing that you could do, is have an attack, identify it, and then just not do anything about it. And these defensive strategies are just good defensive strategies in security in general. They're not specific to just SCADA systems themselves. Some other security strategies that you can implement to protect these systems, or just systems in general, or network segmentation. So dividing a system into distinct zones and securing the most critical ones most strictly. So you may have worked with systems that are very secure, but also very frustrating to work with because they are so locked down. So you want to be able to identify the systems that are most critical and make those have the most strict security measures. That's not to say other parts of the system shouldn't be secured or have strict security measures, but you want to at least create some type of prioritization because of how just complex ICS and SCADA systems can be. You also want to keep up to date on your patch management. So updating systems with new vendor software to mitigate the latest vulnerabilities they've been made aware about. So a lot of those updates you might see are just security fixes. You want to keep up to date on those because some of the security fixes might not say it, at least outwardly, on the update, but some of them might be severe and critical. And if the vendor's able to patch them, you definitely want those updates. You also want some type of intrusion detection, so just monitoring system activity, say with your data historian, and being able to detect likely suspicious behavior. So if you see some suspicious behavior, saying it looks like there may be some false data coming from one of your PLCs, you might want to look into that and not just assume, oh, it's a glitch or something's wrong. You shouldn't just not worry about it. You also want to conduct routine security audits on these systems. So they help update aging policies and avoid complacency with the operators. So just assuming that everything's been fine for a while, so it's probably going to be fine. You want to keep auditing these systems just to make sure that maybe something flew under the radar. And you want to catch that as soon as possible. And just in general, you want general just security awareness. So things like trainings, and just being able to set just basic security expectations from everyone involved in the operation. Everyone from the engineers to the operators to the management, just making sure everyone knows their role is on the same page about how to protect the system and keep it safe and running. Because again, they're very complex and there's a lot of machinery and a lot of people involved. And putting these all together can make security difficult, but just if there's some basic practices, we can avoid a lot of vulnerabilities and mitigate a lot of attacks. So at this point, say now it's your turn. So I want to bid good luck to everyone participating in our CTF tomorrow, and I really hope this presentation helps paint the broader picture about what the heck is ICS and what is SCADA, and just why these complex systems are just so critical to protect and keep up and running. So I want to thank you, and I hope that you learned something here. And good luck. And so check back in a few minutes. I think our next presentation will be starting at 10:30. So thank you.